So the next thing we'll see is the IPv6 standard for IP addresses. So what we use mostly is IPv4 address, but due to the shortage of IPv4 address, we are kind of in a transition phase to IPv6. We mostly still use IPv4, but you could find a lot of places they use both IPv6 and IPv4 as part of this transition these days. Okay, so eventually the goal is to run only IPv6, but it will still take a reasonably long time. Okay, so IPv4, the one that we saw extensively in module 1, is a 32-bit quantity, so that's what an IPv4 address is, version 4. Now IP version 6 is a 128-bit address. Now in IPv4 we saw there are different classes, class A, B, C, D and so on. So now whereas in IPv6 there's no such class-based addressing. But using the first few bits of an IPv6 address, we should be able to identify the different uses of that address. Okay, and let me see. Well, I have a couple of examples below here, but let us first see the notation, how we represent an IPv6 address. So the IPv4 address is represented in the dotted decimal format, as you all know by now. So 143.132.10.1, that's a unicast IPv4 address. So now in the IPv6 standard, we use something similar to how we represent a MAC address. So it's 128 bits. So what we are going to do is we are going to represent things in hexadecimal. So take up this case. So each is a hexadecimal digit. So that means 4 bits. So 4 bits. So that is 16 bits. And another 16 bits, another 16 bits, another 16 bits, and so on. So there are 8 such 16-bit blocks or piece of address. So each digit is hexadecimal digit, so there are 16 bits for one block, so there are 8 such blocks, so 16 times 8 is 128 bits. Okay, so this is how we represent an IPv6 address in hexadecimal digit, and 8 such things. So we separate them by a colon. Okay, now if you want to indicate that of course you're not going to see this in detail, so that's a separate topic. It could be a separate module by itself, but since we're running out of time in this semester, so I'm just giving you some ideas about IPv6. Okay, if you want to indicate that this is a globally unique unicast IP address, then you have 001 as a prefix in this for this IPv6 address. So if you start with 001, then it indicates that it is, of course this is in binary, so if the first hexadecimal digit starts with 001, then it indicates it's a global unicast IP address. Now if you want to indicate that it is a link local use address, so the link local use address is something like this. That address will be unique only within the network, so it's like almost like a private address. So that means it could be reused in another network. Okay, so the link here really mean network, so it is local within a network and it will be reused in another network. Okay, whereas the first one, it's a globally unique unicast IP address, so it has to start with 001. But if you want to indicate that it is like a private address, link local use address, you use this as the prefix in binary for an IPv6 address. Okay, now also if you want to indicate that's a multicast address, you could have these 8 consecutive ones like this as part of as the first as a prefix for IPv6 address. Now there's something called the IPv4 compatible IPv6 address. So especially during this transition phase, as people are still using IPv4 address, we can come up with something called an IPv6 equivalent or IPv6 compatible version of an IPv4 address. So it's called IPv4 compatible IPv6 address. So let me illustrate that with an example here. So let us say this is our IPv4 address, and how to get an IPv4 compatible IPv6 address. So what we need to figure out is, so as we know, IPv6 is 128 bits, right, and IPv4 is 32 bits. So we will prefix the IPv6 address with the remaining 128 minus 32, 96 zeros. So it will be 96 zeros and followed by this thing written in binary. So 143 is this is 132, this is 10 in binary, and 45 is this is in binary. Now you will really have 96 zeros followed by this 32 bits in binary. Now if you want to indicate this in hexadecimal, you could say 0000, then colon 0000, because you could indicate like this. So you could say 000 for the first 16-bit zeros, then another 16 zeros, another 16 zeros, another 16 zeros, another 16 zeros, another 16 zeros. You need 6 such blocks of 16-bit quantities, that will be the 96 zeros, followed by 16 bits of zeros and ones corresponding to the address here. So these 16 bits could be written as 8F84. You see 1000 is really 8. Then these 4 ones is F in hexadecimal. Then again 1000 is 8. Then 0100 is 4. So these 16 bits could be written as this one hexadecimal unit. Then colon, again you have 000, that is 0 in hexadecimal. 1010 is 10, so that is A in hexadecimal. Then 0010 is 2. Then 1101 is D. Okay, that is like what, 13. So we could, as I said, put all 0, 16, 0000 colon 4 zeros, another 4 zeros, and so on. Now there's a shortcut notation, so that's what we indicate with 2 colons. So instead of putting all zeros like that, we can put just 2 colons. That means we can use it only once in an IPv6 address. So if you want to indicate some consecutive zeros, you just put the 2 colons, and whatever follows that together with those zeros will make up 128 bits. Okay. So even if you have these 16 bits as zeros, you could put just 2 colons and put 0A to D. So that means this 16 bits is only the kind of non-zero quantity, even though there's a 00, but it's not like consecutive zeros. So you could put 2 colons and just the non-zero quantity that you want to write explicitly in hexadecimal. So that's like a shortcut notation of writing an IPv6 address. So as part of an exam question, I could ask you this. So given an IPv4 address, come up with an IPv4 compatible IPv6 address. So this is the method you will use. So write basically the IPv4 address in binary and then convert them into hexadecimal by looking at every 4 bits. Okay. Any question? So for example, the 2 colon case I indicated here. So if this is, say, the IPv6 address, you have 47CD followed by these consecutive zeros and then A456 and 0124, then you could really shorten it like this: 47CD, then the 2 colons, then the A456, then 0124. So any router will be able to figure it out how many zeros are in between if it is sent out like this. Okay, so the 2 colons can be used again only once in an IPv6 address. Now you may be wondering about how communication can happen between, say, an like something like scenarios like this. So you have two IPv6 networks, and everything in between is an IPv4 network. Okay, so as we do this transition, the routers should be able to handle both. So especially the router that's attached to an IPv6 network and an IPv4 network should be able to handle both an IPv6 address as well as an IPv4 address. So we already saw this tunneling process that could be used to hide one IP header inside another IP header. It's called IP in IP encapsulation. So for example, here you want to send a message from one IPv6 network to another IPv6 network. So that means we really need an IPv6 header and the corresponding payload, the data that we want to send. So you have a destination address in the IPv6 format. Of course, the source address also will be part of the IPv6 header. So what we need to do is we need to encapsulate the entire IPv6 datagram inside an IPv4 datagram, because the public internet is kind of majority IPv4. So the router attached to this is called the gateway router. Should be able to generate an IPv4 header corresponding to the gateway router of the destination IPv6 network, and include that address. Say in this case 14.0.0.1 is the destination IP address for this gateway router. Then we should be able to include that as the destination address in IPv4 header, and include this IPv6 datagram as a payload for the IPv4 header. So then the router then will send out to the next hop and so on, and every router in this internet will forward as if this R2 with this IP address is the destination. But once the message goes to this router, it will be able to figure out this is an encapsulated packet, so it will remove the outer IPv4 header, and then it will look at what is the destination address in the inner IPv6 header and correspondingly forward to the destination host. So this is the IP in IP encapsulation process. So we saw that for routing between two private networks and so on. So a very similar process is used here also. Now just a brief introduction about the IPv6 header. So this is how an IPv6 header will look like. So it will have the version field for 4 bits, so it will indicate it is 6. Then traffic class. So even though IP is best effort based, you could provide different types of service to the packets. So the sending source can indicate the kind of service it wants for the packets, and there's a code, it's an 8-bit quantity that can be specified, and the routers should be able to provide that kind of service. And the source and destination could also establish a session, and the packets could be kind of marked with a label indicating what kind of application this packet is belonging to and so on. So this is kind of what is called quality of service. So if you want the packets to be provided certain level of service or certain specific service as it gets forwarded across the internet, then you can use this traffic class and flow label. But it's not very commonly used because routers provide best effort service, and only if you want to forward packets that are specifically destined for certain applications, then you can use this the traffic class and flow label. Then the payload length is again capturing the length, the amount of information you're including in the you're including as part of the header. So the header length, so 16 bits. So you can include up to 2 to the power 16 minus 1 bytes as part of the IP header and its payload, which is the data portion. So everything put together can be 2 to the power 16 minus 1 bytes because it is 16 bits. So the payload length indicates the amount of bytes you have in the IP header plus the payload. Then the next header field is what I mentioned earlier also. So after the IPv6 header, you could typically have the TCP header because that's the next higher layer protocol that needs to process the packet. But if you want to do some fragmentation, include a fragmentation header, or if you want to do some source routing, indicate this is a sequence of router IP addresses the packet should go through. You could include all these things here as in the next header. So if you want to say include some details about fragmentation, then include a particular code value indicating it's going to be a fragmentation header following the IPv6 header. Then in that header, so I have a slide I think here, yeah, so something like this. So after if you want to indicate the packet should go through a certain specific sequence of routers hop by hop, you could indicate 0 as the next header value, and that is the code for the hop by hop header. And after the routers process this header, if you want them to process something else regarding fragmentation, you could include the code for fragmentation, which is 44, and that could be included here. Then after the fragmentation header, then you want to specify the next header to be processed as a TCP header. You include the code for this. So when a router sees the code 6, it means it's a TCP header, so the router will not process beyond this, because TCP is an end-to-end protocol, so the routers are not supposed to process a TCP header. Only the source or destination host will be able to process a TCP header. So that's actually the next module we are going to look at in detail. So this way, using the next header field, we can include all the different things. In the IPv4 header, we don't have this explicitly, we just have options, and this is not organized there like this. So here it is more organized. You could specify the sequence of next header field values and the corresponding whatever you want to do, specify in those headers, and then specify what's the following header and so on. And then you have the hop limit, that is the TTL here, time to leave. So again it's 8 bits, so you limit the number of intermediate routers network the packet can go through. It is still 2 to the power 8 minus 1, 255. So every time a router gets a packet, it will decrement the hop limit, and only if it is not 0, it will forward it further, otherwise if it will drop the packet. Then the source address is the IPv6 address of the sending entity, the source. So it's 128 bits. So you have 38 bits, 32 bits in each row. So that's why you have like what's 1, 3, 4 rows. Okay. So again, it's linear. Just for visualization, we're representing the 32-bit rows like this. Similarly, the destination IP address is the 128-bit IPv6 address. Okay. And then the next header, which is what I showed here. So if you do not include, so these are called extension headers. So if you do not include any extension header like this, you simply specify 6 as a value for the next header field. That means the header following the IP header is going to be TCP header and the TCP data. Okay, so alright, so with that we finished this module. So I'll convert this to a video. If you have any